Now, we are going to change this to, instead of use a graphing calculator, to without a graphing calculator. Graph. Without a graphing calculator, graph y equals log base 8 of x. So we need to know how to graph all of our log graphs, and this would be a parent graph for a log graph without our calculators, and we're going to need to do all of the transformations with them as well. So how do we graph a log function? Well, all log graphs are going to go through the point 1, 0. And since the base of this one is 8, this one's going to go through 8, 1. So we always have a point that is the base, 1. Because if you think of it, if I plug in 8 for x, 8 to what power is 8? 1. And that's why we have the point 8, 1. Log graphs all have an asymptote at x equals 0. Whoa, that point big enough so it goes through it. There we go, perfect. And that's the shape of our log graph. And again, our log graph is an inverse, and this graph would be an inverse of y equals 8 to the x. And that's a reflection over the line y equals x. So it isn't hard to graph this without a graphing calculator, and we'll be expected to be able to graph all of our log graphs, and what we're going to do in the next couple of examples is draw some graphs with all of our transformations. Now, identify the intercepts. The only intercept, we have an x-intercept at 1. There are no y-intercepts. What's the domain and range, and what's the asymptote? Well, the equation of the asymptote is x equals 0. Our domain are just the positive x values. X is bigger than 0, but not equal to 0 because there's an asymptote there. And our range is everything. Now I'm going to get you to, well, first of all, on the next page, they list how to work with transformations with logs. They have a bunch of different letters here. Again, what we're going to look at is we're going to look at moving everything to the right hand of the equation, and just like we did in transformations, instead of memorizing all of this, we are just going to work from left to right. I mean, that looks like a pretty easy thing to memorize. You've sounded out, it probably makes some kind of is easy word to remember, and then you would know what to do. Or we could just work from left to right. I think working from left to right will be easier. So on page 400, which is a blank page, we're going to add 2 more examples. Here's our first example of transformations. Graph y equals 4 log 3 of x plus 1 plus 5. So the first thing we need to do, just like when graphing exponential functions, we need to recognize what the parent graph is and draw a quick sketch of this. The parent graph of this one is log base 3 of x. And so our quick sketch off to the side here, we know that that has an asymptote at x equals 0. All logs go through 1, 0. And the base is 3, so this one will go through 3, 1. And it has this shape. Now we're going to take those 2 points and that asymptote and work from left to right to draw and figure out where those points are going to go. Again, what I like to do, just like I did with our exponential graphs, what makes this a little bit harder is this number 3 is part of our parent function. So if I go to my equation here and I put maybe a box around all of the things that are part of my parent function, that's going to remind me that I don't need to do anything with that 3. That 3 is not going to be a transformation. When moving from left to right, I'm going to hit the 4, then the 1, then the 5. And when we set up our points, so we have 1, 0, 3, 1, and our asymptote x equals 0. Moving from left to right, we always did our stretches and compressions first. So when we go from left to right, we hit the 4. That's going to be a vertical stretch. It's going to multiply our y values by 4. Do we have a horizontal stretch in this one? No. So that, in our first thing, the only thing we're going to do is multiply our y values by 4 and get those 2 points. Then we always did our translations together. Moving from left to right, now we'll hit the 1 and then the 5. The 1 is going to go left 1. The 5 is going to go up 5. So if we go left 1, we'll be at 0 and 2. Up 5, we'll be at 5 and 9. What is the only thing that's going to affect our asymptote at x equals 0? The left and the right. So in this case, we do move left 1, so our asymptote is going to go to x equals -1. See how similar this is to when we graphed our exponential functions? We did the same thing with our points, same thing with our asymptotes. And now we can draw the sketch of our graph. We know that our asymptote got moved left 1, so we have x equals -1. We can label the point 0, 5. And 2, 9. Once we have those 2 points, draw the shape of your logarithmic graph going through those 2 points and approaching your asymptote. And there's the graph of y equals 4 log base 3 of x plus 1 plus 5. We'll do one more example on this page. Everybody ready? We are going to graph y equals 2 natural log of 1/2 x plus 2 minus 3. Why did I choose this one? Because a natural log, because it makes people feel uncomfortable with something so natural, maybe. I don't know. Natural log always seems harder because what is our parent graph? Our parent graph is the natural log of x. And although it's identical to every other log graph in that it has an asymptote at x equals 0, it has a point at 1, 0, and the base is e, it has a point at e, 1, but that e is just different. Instead of using a number, well, it is a number, it's 2.7, but it's not a nice whole number like we're used to. But other than that, is exactly the same. It's the other reason I chose this one. What other thing do I want to remind you about? Okay, it has a horizontal stretch, so we want to, that we have to multiply our x values by 2. That is one thing. And we have to factor it out because we have a horizontal stretch and a horizontal translation at the same time. So before we do anything, we're going to rewrite this question. I'm going to use 2 sets of brackets. Have to factor out the x. Whew. And that's where things get tricky. How do you take a half out of 2? It's going to be 4. So instead of trying to take a half out of 2, because that sounds awkward, or it just sounds like it's not easy, I instead think, well, if I would redistribute this, what would have to go in that space so that I get a plus 2? And then it becomes much easier to see that that number has to be a 4. I mean, taking a half out of 2 is basically saying if you have 2 and you break it up into halves, how many would you get? You would get 4 of them. 4 halves make up 2. But somehow factoring a fraction out of a number is harder to think about. So it might be easier to write a space there and say, if I multiplied it through, what number would I have to put there so I would get the 2 that I had before? And 1/2 times 4 is equal to that 2. So now that it's in factored form, we can take our 2 points, 1, 0, and e, 1, and our asymptote at x equals 0. And moving from left to right, we have a 2 and then a half. So that'll make our y by 2 and our x by 2. So when you multiply e by 2, you're going to get 2e, which, again, it's a little bit more awkward than a number, but it's the same idea. And then continuing to move left to right, we hit our translations next. We've got a 4. That's going to go left 4. The -3 is going to go down 3. So our first number is going to be nice to graph, -2, -3. I think we're pretty confident in that. Our second number, not so nice to graph. We're going to have to estimate that a little bit. The last thing we have to look at is what's going to happen to our asymptote. Well, again, the only thing that's going to affect our vertical asymptote is if we move things left or right. Did we do that? Yes, we moved left 4. So our asymptote will be at x equals -4. So when we go to graph this, we can start by graphing our asymptote. We can graph our nice point, -2, -3. And then our not nice point is 2e minus 4, comma, -1. Well, if e is 2.7, using that as an estimate, 2 times 2.7 is going to be 5.4. 5.4 minus 4 will be 1.4. So when I go to graph this, I'm going to put a point at 1.4, comma, -1. I'm still going to label this as 2e minus 4, comma, -1. But then I'll have a good idea of where that point would be. And there is our final graph. Okay, so after question 2, we'll just graph 7a. And I think, let me just check here. It says use a graphing calculator, but I want you to do it without. And 7a just deals with nice graphs, just parent graphs.